We're going to finish this chapter 26 on AVO trees. AVO trees are binary search trees. They are specialized binary search trees. In AVO trees, all the nodes are balanced. By definition, balanced means the balanced factor is 0, -1, or +1. The definition of the balance factor for each node is the height of its right subtree minus the height of its left subtree. We introduced the techniques for rebalancing a tree after insertion and deletion, and we looked at the design of the AVO tree last time. So I think what I'm going to do today is just look at one more thing here is on the implementing the delete method. And then we're going to look at the entire class for AVO tree and some design and implementation details. And so finally, we're going to look at the analysis to get the time complexity. So I'm going to start now with this implementing the delete method. When you delete an element from an AVO tree, you do the same thing as you delete in a binary search tree. So what happens is that after this, the tree may not be balanced. So you need to perform rebalance. Let me show you the diagram. So I'm going to open another tab, and this is very helpful, and you see how it actually works and using this visual animation. So I'm going to bring up this animation. So this is the animation right here. So what I'm going to do is this. I'm going to delete this 80. So you delete the 80. After this is deleted, and the tree is not balanced. See what happens. You can see this is the, and here is 35, 25, and go all the way to 50. So this, the node 50, the balanced factor becoming -2. All right, so let's see how we're going to do it. Remove 80. And so here we're going to find 80 and then delete it. Okay, so when you delete this 80, and here is the case. There's two cases when you delete it in binary search tree. The case one is 80 does not have a left child. So in this case, that's the case one. So 80's left child is null. So we're going to remove 80 by connecting 80's right child, if any. So 80 doesn't have any right, is null. So this is the after 80 is removed, and the right, the pointer from 50 is null. All right, so we're going to delete this now. And then after this, we're going to perform a rotation at this 50. So 50, we're going to perform this rotation. It's left heavy and right heavy. So LR rotation. So after LR rotation, you're going to see 35 is now becoming the root, and 25 and 50 are the left and right child of 35. All right, so this is how it works. So back to this. implementing the delete method. So we're going to look at these two cases, and for each case, after you're done, you need to go to perform this is the balance path. So performing this balance path and to rebalance the tree. So this is what we need to do. Okay. All right, so now we're going to look at the entire implementation for the aviator tree. So aviator tree extends BST, and it has the constructors very similar to BST. Has the constructor. You're going to specify a comparator, or you can use the natural comparator. You can have this no-arg constructor, and also there's another constructor is to take an array of objects and put it into aviator tree. And so please note that this override this create new node. So this create new node, and here is now we're going to create new AVL tree node. So this is the one we're going to have. So this create new node in the BST, you're going to just return the tree node. But in this case, for the aviator tree, we're going to return aviator tree node. So when you do insert, look at the insert here. So what you do is you're going to invoke super.insert e. All right, in this super.insert e, so if you go back to open another tab to look at the algorithm for BST, and let's do that. I'm going to open another tab and to look at the algorithm for this one here, for this. I'm just looking at directly to look at the code for this BST. So this is the BST class. So let's look at the code for BST class. And now you're going to see this insert. When you do this insert, so here is the BST. Okay, well, BST is implements. There's a tree interface. All right, so this is search, and this is the insert. Do you see the insert right here? And this one is create new node. So that's here. If you are in the aviator tree, you invoke the insert. This create new node by dynamic binding the polymorphism, and this one is going to create an aviator tree node. So that's really very nice about this. It is here. It is because of here. You have this defined using this method, create new node. If you hard code this in the BST, so here, if you hard code this in BST, and right here in the BST, this is BST. Instead of using create new node, okay, if you hard code this new tree node, okay, and this will only work for BST. And when you come to the aviator tree, it's not going to work because now you're creating which node is tree node. So I need to have this is aviator tree node for the aviator tree. So this comes very nice. We have this create tree node method for this purpose. All right, you can look at the rest of the implementation, and so it's pretty much straightforward if you follow the algorithm. Okay. All right, so let's continue now to the next. We're going to look at this writing a test code. So you can write a test code for the AVO tree. And so this is to create AVO tree and using an array of integer objects. And now you can print all this tree here, and this is the print method, print tree. So this is BST. Now this is fine because AVO tree is subtype of BST, so we can have this is here. Actually, we can do a little better here. So I'm gonna do a little better, but because I'm using here is integer. Okay, here are integers, right? So this should be fine. I'm gonna just make it a more specific integer. Okay, so here's BST integer. And so this is the integer I'm using. Okay. All right. So you print this, okay, and print the in order and post order, pre-order, so all here. Okay, so this is the AVO tree. See how you insert after insert and after this the delete, and see how this is what is tree. So to display the tree and print the tree. And this is here to use the for each loop and for this AVO tree. And because AVO tree is subtype of the BST, and BST it's iterable, and using this the in order to iterate all the elements in the BST. All right, so here you can follow the diagram and see the test result, and here this diagram. And next, let's look at the time complexity analysis. So the time complexity analysis, it's not difficult to see here. Is you're gonna look at the height. So let's just do a very simple thing here. Is let GH denote the minimum number of nodes in an AVO tree with height h. So with height h. All right, so please note that the definition for the height is if the tree has only one node, the height is 0. So if the tree is empty, the height is -1. Okay. So obviously here, if G0, if the height is 0, so you have only one node. If height is 1, so you have 2 nodes. So height is 1. It's the minimum number of nodes. You're gonna have this 2. 2 is the minimum number. You could have maximum is 3, so it's minimum. The minimum number of nodes in an AVO tree with height h greater than or equal to must have 2 minimum subtrees, one with height h minus 1 and the other with height h minus 2. So this is what we have, is GH is the minimum number of nodes, okay, in the AVO tree with height h is G h minus 1 plus G h minus 2 and plus 1. So that's the one is the root itself. And this is actually, you see it's a Fibonacci number. It's actually very similar to Fibonacci number, except without plus 1, but it's essentially the same. And that is, you can obtain it. That is this, what is h? H is going to be less than, and this number, that is a log n, in order of log n. So h is order of log n. And that's the analysis of time complexity. All right, that is all for this chapter on AVO tree. I'm going to now review the programming projects in this chapter and also the previous chapter. So let's do this first. I'm going to open another tab. So I'm going to go to this. Another tab. So here in the preceding chapter, binary search tree, we have this programming project here, right here, and they're due. I think it's 16th and Monday, so it's due on Monday. All right, let's look at all this now. So here's the first one. Define a new class named BST with height that extends BST with an additional method. The additional method is the height. So you need to return the height of this binary tree. So this is here. And use this template. So I'm going to open this template now. And this is the template. Here, we're going to open it. All right. So this is the one here. This is exercise 25_01. All right. So, and please read this code. So how we write the test code here. And this, the BST with height. So you create a tree and see what is the tree height, the empty tree. So what is height, all this, and do all this work here. All right, so now what you need to do is to do this. And you scroll down, you can see this is the this one here. The last one is this class BST with height extends this. All right, so here we have the constructor, we have the constructor, we have this another constructor, and this is a height. So I already give you the hint here. You can write this the overloaded height method. So this is the height starting from the root, and here is height start from any node here. And you can write this code here. This one is going to be writing recursive code. So writing recursive code, how do you get the height for this entire tree? It's the look at is 1 plus the maximum height between its left subtree and the right subtree. So it is here. That's all you need to write. Okay. So please look at it. If you still have a question, and just email me, and we can continue to discuss it next time in the class. All right, so let's look at the next one here now. The next. All right, the next programming project here is this test perfect binary tree. A perfect binary tree is a complete binary tree with all levels fully filled. Even the last level, it's completely filled. All right, so you're going to define a class named this BST with test perfect, and that extends BST with the following method. So here is the method. All right, so this is the method is perfect BST. So there's a hint here. The number of nodes in a perfect binary tree is exactly in this. So this is going to be the number of nodes here. All right. So we're going so what you need to do is you need to use the one from the previous exercise. You need to find the height of the tree. Okay. So here I'm going to copy and paste this. And to see, you need to use this template. So I'm going to use this template. All right. So look at this test code here, the template. And so scroll down all the way down to see this BST with test perfect extends BST. So here, this is the one you already done from the previous exercise and copied here for the height. So now you can write the code is perfect BST. So that's already, hint is already given to you. So you just see if that's the number of nodes are correct for it to be a perfect binary tree. All right, next. This, we're going to define a new class named the BST with number of non-leaves that extends BST with the following methods. So you need to write this method to get number of non-leaves. So in the binary search tree, number of non-leaves. So the leaf is the one without any children, and non-leaves, so all the others are non-leaves, right? So that's, we need to find that number. So you need to write this code. So again, this test code is given to you, and you can look at this test code. So I'm going to copy them. So all the way scroll down and see, we're going to write this test code. Yeah. So it's BST with number of non-leaves, and this is the one get number of non-leaves. So we're going to define a help method, and this one you can use it writing this using recursive. So do it recursively, you can find it. All right. Okay, one more, last one in this chapter. So this one here is to implement set operations in see, I got it wrong. It's in the yeah, in the tree here. So this should be a change this to this in the set operations in tree. So this, let's look at this now. I'm going to look at this template. So I'm going to implement the methods contains all, add all, remove all, retain all, and to array. So this in the tree interface. So we need to do this in the tree interface. So I'm going to show you here in the tree interface. It is this. So here, the code here. So we have this is the test code. So we're going to prompt the user to enter this strings and put it into array, and then we create the BST. All right, so here. All right, so then we're going to do this the operations. So look at this operations we have is the here's add all, remove all. You're going to see this retain all. So these are for the trees here. So go all the way down here. You're going to see this BST implements tree, and this is tree extends. Let's go down here. You're going to see that tree here. So this is the tree here. Interface tree extends collection. So collection has all these methods, add all, remove all, retain all, contains all those methods. So these are the methods we need to implement. So contains all, add all, remove all, retain all. So to array. So there's another to array, and so we need to write this both. Okay. All right. So all this here, it's very similar to the exercise we have already done for the my list interface. So it's and here. So this one here it's in tree. All right. So this the methods. So there's two array. There's two array. There's another two array methods. So I'm gonna have to make the correction in this here. All right. So just note that this is the implement set operations in tree. All right, so now let's look at the exercise here in the aviary tree here. In the aviary tree, we're going to write this program exercise, and here, this one. So what we need to do is this: a test aviary tree. It's a binary search tree. So we're going to define a new class, myBST, that extends BST with the following method. Is this is aviary tree. So we want to test if this tree is an aviary tree. So here is the test code, and here it's here in this right here, and you can look at the test code right here. All right. So this is the test code, and here, and this is template, and all the way down here. The last one here is my BST, extends BST. And so we need to see if this is aviary tree. For this to be aviary tree, you just have to look at every node to see if they're balanced. So if they're balanced, and that's the aviary tree. If any one of the node is not balanced, it's not aviary tree. So that's what you need to do. All right, in this. Okay, so you need to study all this and write the code. And if you have questions, email me. And if it's if many people have the same questions, so we're gonna address it in the class. All right. Any questions? Any questions? All right, I'm going to stop recording.